Welcome to ECE 376 Embedded Systems, lecture number 18, Timer2 Interrupts. Now, so far we've been looking at writing code in C and assembler. The problem with what we're doing is there's only one processor, so that you can only do one thing at a time. For example, I can keep track of time, I can drive an LCD display, I can play frequency, but I can't do two things at once. Second problem is timing is very difficult to do in assembly and in C. In assembly, for example, if I want to have a 10 millisecond wait routine, what I could do is set up a loop so that I burn 100,000 clocks. If I do it, this inner loop has 1, 2, 3, 4 instructions plus 1 for go to, 5 times 250 times 80. Set up these loops and eventually get the timing so it waits 100,000 clocks or 10 milliseconds. I can do the same thing in C. In C, just set up a for loop. Each loop takes so much time. This 6170 is kind of used in an oscilloscope or guess again until I get this to be 10 milliseconds. Then I can have this loop wait 10 milliseconds and likewise have a timer that counts every 10 milliseconds. That you can do. There's a couple of problems with that though. First, the timing is still slightly off. It's hard to get the loops to be exactly 100,000 clocks. It's inefficient. Almost all the time is spent in the wait loop. So rather than doing things like driving the display, reading the sensors, doing other stuff, I'm just wasting time spinning my wheels. In addition, it makes it really difficult to change the code. If I were to take this previous routine and modify it in any way, such as drive the LCD display, read a sensor, that changes the loop, which changes the timing, meaning I have to change the for loop. So what we've been doing doesn't work real well. There is a way around that. These are called timer interrupts. Interrupts solve all these problems. Interrupts are similar to a subroutine except that they're called by hardware. So subroutines are called by software. Like every time I want to update the LCD display, I'll call LCD write. Interrupts, on the other hand, are called by hardware. Every 10 milliseconds or so, it's going to be called. Actually, every n clocks, it'll be called. That's extremely useful. Kind of one way to think about interrupts is sort of the way classes are handled. One way is polling. I could sit there and stop every 5 minutes and go through the class one by one and ask if there's any questions. Continue on the lecture for 5 minutes, stop the class and do polling, ask every person one by one if there's any questions. Really inefficient. A better way is actually the way we run classes. I give the lecture. If somebody has a question, they raise their hands. And then we stop the class, handle the question, then go back to where we left off. That's an interrupt. When the processor is running along doing the main routine, then the interrupt happens. Say 10 milliseconds happens. I'll stop the main routine, do something, like increase the counter, then go back to the main routine. That's an interrupt. This is called by hardware rather than software. That makes it really powerful, also really strange. What you've got is somebody else calling subroutines in your program. And I'd like to be able to pass data back and forth to the subroutine, but I didn't call it. So there's other techniques they have to use, like using global variables. Now timers are extremely useful. So likewise, there's 4 available on the PIC processor. Each one's slightly different because as soon as they have one interrupt, people say, hey, this is useful, can I have 2? So they add another one. Then people ask, hey, the 2's not enough, can I have more? So each one will be slightly different. We're going to start with timer 2. For each interrupt, every n clocks, I stop the processor, stop the main routine, and do something. For timer 0, n can be anywhere between 1 and 2 to the 24th, so it maxes out at 1.6 seconds. Timer 1 and 3 can go up to 2 to the 19th clocks, or 52 milliseconds. And timer 2, the one we're looking at here, goes up to 2 to the 16th clocks, or 6.5 milliseconds. So this is what happens with interrupts. Interrupts are by default turned off. Likewise, we've been ignoring them up to date. You have to turn them on to use them. If an interrupt happens, like n clocks go by, what happens is the current instruction is completed, and that's the current instruction in assembly, not C. The processor then inserts a call address 8. It jumps to the interrupt service routine at address 8. That's hard-coded. And the interrupt service routine must likewise be located at address 8. then what happens on an interrupt? When an interrupt happens, I have to save the W in status register. Again, the interrupt can happen at any time in the program. It could happen right in the middle of an if statement. So what I need to have is the if statement executes the same regardless whether or not the interrupt happened or not. So I've got to save the W in status register. Then at the end, I have to restore W in status. So the processor is in exactly the same state it was when the interrupt was called. Optionally, I can do something. Then I exit. And when I exit, I do a different return. This isn't return from subroutine. This is a return from interrupt. That's a special command in assembly. What it does is it restores the W in status registers, pops the return address off the stack, and then goes to wherever I left off in the main routine. So in order to get an interrupt to happen, there's a couple things you need to do. First, I have to set the condition for the interrupt. Then I have to enable the interrupt. And inside the interrupt routine, I have to acknowledge it. So what happens is if the interrupt is turned on, the flag gets set. If the interrupt is enabled, that'll trigger the interrupt. If I don't clear the flag, what happens is as soon as I exit the interrupt service routine, it's going to say, hey, the flag is set, and it's going to call the interrupt. When it comes back, if the flag isn't cleared, it's going to say, hey, the flag is set, call the interrupt. So you're stuck inside the interrupt service routine. You got to clear the flag. The conditions for the interrupt, as I interrupt every n clocks, where n is a times b times c. A is a number between 1 and 16, stored in T2con. B is a number 1 to 256, stored in PR2. And C is a number 1, 4, or 16, also stored in T2con. So this is what it looks like when an interrupt is running. I've got a main routine that's just displaying a count. In the background is the interrupt service routine. The main routine is looping, displaying data over and over again. Every millisecond, the interrupt service routine kicks in and increases the counter. So what I'm left with is time accurate to 1 millisecond. In addition, on RA1, it's toggling a bit. So I can play a precise tune. So you can kind of hear the 500 hertz. I can play precise frequency or keep track of time. That's the second thing I can do in addition to whatever the main routine is doing. So that's kind of what interrupts do. They run in the background. They have no effect on the main routine. The main routine has no effect on the interrupt. They basically steal cycles. So the procedure to turn on the interrupt, once I set the condition for the interrupt, I have to enable the interrupt, and here there's actually 5 enable bits. I have to turn it on, really turn it on, honestly turn it on, then a global turn it on. 2 of these kind of make sense. I want to be able to turn on timer 2 interrupts, plus there's a global interrupt enable. There's other interrupts we're going to be getting to later. I might not want to turn on all the interrupts until I'm ready, so the global interrupt enable kind of makes sense. The enable for each interrupt makes sense. Why I have to enable it 4 times, I'm not sure, but that's just the way it is. In addition, I have to set the condition for the interrupt. That's your n, which is a times b times c. N is stored in 2 bytes. T2con stores a and c. PR2 stores b. And the encoding is that the 4 bits of A3, A2, A1, A0, determine A, and it's this binary count plus 1. The reason they do that is since you're multiplying, 0 times anything is 0, so they shift it by 1. 0 means 1, 1 means 2, 2 means 3. So A can be 1 through 16. B likewise is an 8-bit number. To avoid 0, they offset it by 1. 0 means 1, 1 means 2. So this represents the numbers 1 through 256. And C is kind of the oddity. C is just 2 bits right here. Those 2 bits can represent either 1, 4, or 16. So that's how you set N. You set T2con and PR2. As an example, if I had the following code, this isn't the whole program. This is just the 2 most interesting parts. I've got the interrupt service routine. That's at address 8. And then the initialization. Once I turn on the interrupt, then every n clocks, this routine is called. So if I want to max it out, I'm going to make A equal to 16, C equal to 16, B equals 256. That works out that n is now 65,536. or 6.55 milliseconds. 1 clock is 100 nanoseconds on the PIC processor. Plus I turn it on, turn it on, turn it on, really turn it on, honestly turn it on. Now timer 2 interrupts are running. Inside the interrupt service routine, every time it's called, I'm going to toggle port C pin 0. And this is what you see. Port C pin 0 toggles. It waits 65,000 clocks, or 6.5536 milliseconds. Toggles again, then waits 65,536 clocks, toggles. So I'm toggling every 6.5 milliseconds, 65,536 clocks. In addition, that creates a square wave of 76 Hertz. The period is twice that number, 13 milliseconds, because for 6 milliseconds I set, 6 milliseconds later I clear. I need 2 toggles to create a square wave. And 1 over 13 milliseconds is 76.28 Hertz. Now, if I want to do something more useful, like keep track of time, I can use timer 2 interrupts. I can have time displayed or recorded every millisecond. To do that, I want n to be 10,000. So 10,000 times 100 nanoseconds gives you 1 millisecond. Interrupt every 10,000 clocks. One way to do that is A is 10, C is 4, B is 250. So to encode A to 10, I input the number 9, 1001 for A. C is 01, meaning 4. That gives the net binary number of 4D. So T2con is 4D. PR2 is 249, meaning 250. And if I do that, this is what I see. Port C pin 0 toggles every time. And I see a nice clean 500 Hertz square wave. It gets 1 millisecond high, 1 millisecond low, gives you a 2 millisecond square wave. And that's what you see right here. The bottom rung is my counter. Every time I interrupt, I'm going to increment a counter, then display it. And here you see the time is displayed to every 1 millisecond. The upper one is every time I loop, I count. The loop is really, really slow. That means the main routine is not keeping up. That doesn't matter. The interrupt runs in the background. The interrupt isn't affected by the main routine. Every millisecond, the interrupt is being called and increments a counter. And the main routine then displays that counter. That's my time in milliseconds. In addition, over here, I'm toggling RA1 every time I interrupt. If I send that to a speaker, you can hear a 500 Hertz sound. If you have an oscilloscope, you can display that. If you don't have an oscilloscope, you can do an app called Piano Tuner. So there's my Piano Tuner app. It's displaying the frequency. That's 500.7 Hertz. So that's kind of one trick. If you don't have an oscilloscope on hand, what you can do is the same thing I did here. I just took an output pin through a 200 ohm resistor. That drives the speaker, then the other pin goes to ground. And you get a nice, well, as long as the ground doesn't fall out. Turns the square wave into a sound. Then using a Piano Tuner app, I can tell you what the frequency is. It's kind of annoying. I can output other frequencies. If I want to output a certain note, like play 440 Hertz, I just change n. So instead of being 10,000, I make it 11,364. And the way you calculate it, it's 10 million. The PIC does 10 million instructions per second, divided by 2, divided by frequency. The reason for 2 is I need 2 toggles per cycle. And this is 1 over 440 Hertz. This is 1 over 440 Hertz. It gives you 11,364. Find some combination of A times B times C, which is close. And this isn't exact, but this is close to 11,364. Change that, so A is 12, C is 4. That gives you T2con as 5D. And kind of a way to do that is, again, go back to here. I want 11, which is 1011. 11 means 12. C is 4, so still 0, 1. Convert that binary number to hexadecimal, and that turns out to be 5D. And then PR2 is 236, meaning 237. Do that, and I now have a 440 Hertz square wave. So here I've took the previous code and modified it so that I'm now doing 440 Hertz. And what you see is this. The timing is off. This is no longer counting in seconds. Again, it's not doing 1 millisecond between interrupts. It's some other time, the 440 Hertz. If I look at the frequency, though, it's dead on. So that's what you can do with Timer2 interrupts. I can keep track of time, or I can output a precise frequency. The other thing to note is this guy right here, T2. This is being displayed in the main routine. It looks like it should never be adjusted. There's nothing changing T2. That's the magic of interrupts. Up here in the interrupt service routine is where T2 is changed. Every time Timer2 is called, every n clocks, T2 gets increased. And that shows up in the main routine when I display it. This is also where, to pass data from the main routine to the interrupt, I've got to use globals. Back in C programming, you're told never, never, never use globals. In this class, always, always, always use globals. The reason is you don't have a choice. I have to pass data to a subroutine that I'm not calling. The hardware is calling this subroutine. There's no way to pass data to a subroutine that I don't call other than globals. Everybody can see globals. The interrupt service routine can see the global variable. The main routine can see the global variable. Likewise, that's about the only way you can get data from the main routine to the interrupt back and forth is through interrupt or through global variables. If you want to draw a flowchart for a program with an interrupt, you almost have to have two separate flowcharts. One for the main routine. On reset, I execute this routine. Then a second flowchart for the interrupt. That's because the interrupt happens whenever n clocks go by. I have no idea where that's going to happen inside the main routine. So likewise, this is almost in parallel. Every n clocks, I'll call the interrupt. What's common is save W in status, clear the flag, restore W in status, then return from interrupt. What's different is once in a while, I presumably call the interrupt for some reason, do something, like increment a counter, toggle a pin. But that's really optional. On the homeworks, when you do the interrupts, what I would do is leave off the pink part, because that's kind of understood, and just every 2 milliseconds when I interrupt, or every n clocks when I interrupt, what do you do? Also notice the style for the interrupt. There is no looping, there's nothing else going on, it's get in, get out quickly. That's because the next interrupt could be happening at any time. I do not want to do any looping inside the interrupts. I just want to execute the code very quickly, then return from interrupt. In terms of interrupt constraints, there's a couple things you can do and can't do with an interrupt. What happens with the interrupt is the main routine is running along, that's the part in blue. Then n clocks happen. That sets the interrupt flag. If it says, hey, the interrupt is enabled, the flag is set, call the interrupt. The main routine stops, it saves W in status, and then jumps to address 8. The interrupt service routine, here in red, then executes. At the end of the routine, it then returns to the main routine. So what's happening is the interrupt is stealing cycles. It's stealing cycles from the main routine, so the main routine actually kind of slows down when I call the interrupt. What this means is a couple things. First off, I've got to make sure that if I interrupt every millisecond, the interrupt service routine has to take less than 1 millisecond. If it takes more than that, I simply don't have time to execute the interrupt service routine. So that kind of sets the maximum rate at which the interrupts can be called. If you do nothing other than the previous code, like toggle a bit, come back, it takes about 50 clocks to trigger the interrupt. What that means is that if I want to measure time to 1 millisecond is 10,000 clocks. Every 10,000 clocks, I call the interrupt service routine and steal 50 cycles. That's stop the main routine, save W in status, jump to the interrupt service routine, do something like increment a counter, restore W in status, return. That takes time, about 50 clocks. That leaves 99 50 clocks for the main routine. 50 clocks are spent in the interrupt for every 10,000 clocks. So the main routine is still running at 99.5% of its speed. It's not bad. If one measure time to 100 microseconds, that means I interrupt every 10,000 or every 1,000 clocks. That still works. I still have 50 clocks at every 1,000, so the main routine is running a little bit slower. It's now running at 95% speed. If I want to measure time to 10 microseconds, that barely works. Half the time is spent in the interrupt, half the time is spent in the main routine. If I want to measure time to 1 microsecond, that's every 50 clocks, or that's every 10 clocks. Every 10 clocks, I still have 50 clocks, which doesn't work. So you can't measure time to 1 microsecond using Timer 2. The best I can do is 10 microseconds. That's kind of pushing it. 100 microseconds is more reasonable, more realistic. So Timer 2, the smallest time I can measure is about 100 microseconds, or n has to be at least 50. On the other hand, the maximum time between interrupts. Well, if I want to do something like toggle a bit every time I interrupt, the maximum is 65,536. That's when you max out A, B, and C. That gives you 6.55 milliseconds. But actually there is no maximum. I don't have to toggle a bit or increase a count every time I interrupt. For example, I could do this. I could say every 10,000 interrupts, I'll toggle a bit. Just add a counter, and then instead of toggling at every interrupt, I'll toggle at every second interrupt, 10th interrupt, 100th interrupt, 10,000th interrupt. So there actually is no maximum. It's the biggest is 65,000 times the maximum counter size, and there practically is no upper limit to how large a number you can count to. So I can go as slow as I want, but there is an upper limit. I can only interrupt practically every 1,000 clocks or 100 microseconds. In terms of interrupts, interrupts are really picky. They're really annoying, which is why we've ignored them so far and turned them off. Once you turn them on, a very common effect is the processor quits working. This, for example, is code which toggles port CPIN 0 every 1 millisecond. If I write the code and forget this line of code right here, forget to clear Timer 2 flag, then what happens is as soon as I trigger the interrupt, I'll go into here, toggle RC0, exit. As soon as it exits, it says, hey, Timer 2 flag is set. Halts the main routine, calls the interrupt, toggles RC0. Comes back and says, hey, the flag is still set. Halts the main routine, jumps to the interrupt service routine, and toggles RC0. What winds up happening is RC0 is toggled every 50 clocks, the maximum rate at which the interrupts could be called. And the main routine basically shuts down. I spend all the time in the interrupt, and the main routine never has a chance to do anything. If I forget these two lines of code, what happens is the interrupt still works, RC0 is toggled, but I have no idea how fast it's being toggled. It depends upon last time I ran the processor, what the value was for T2 con and PR2 the last time I wrote to them. And if I don't initialize them, I don't really know what they are. So it works, but I have no idea what the timing is. If I forget the enable bits, forget any one of them, then what happens is Timer 2 interrupts are not enabled. If they're not enabled, I never interrupt. If I never interrupt, RC0 never toggles, so RC0 doesn't change. So any mistake whatsoever and the interrupts don't work. That's part of the reason on Bison Academy there's some sample codes. It's a lot easier taking code that works and modifying it. So for example, if I go down to Timer 2, where are we? There we're Timer 2. This is a program that will run. All it does is it sets up Timer 2 interrupts for every 1 millisecond. Turns them on, turns them on, turns them on, turns them on, really turns them on. Every millisecond then, the interrupt service routine is called. It increments T2. Then the main routine just displays what is T2. So what you should see is something similar to this. This will be counting every millisecond. It's not because I modified the code for 440 Hz. But in addition, port A pin 1 is toggled. So if I take that, tie it to a speaker through a 200 ohm resistor, that'll generate a note. And if you take that to your piano tuner, I should see 500 hertz. Again, this one's 440 hertz because I modified the code for 440 hertz. Also note that when you do interrupts, the programming style is this. Don't do anything fancy. Don't do any do loops, while loops, no for loops. Just get in, get out. Again, the interrupt has to happen very quickly because the next interrupt could be happening anytime. If you spend too much time inside the interrupt, you'll miss interrupts. So likewise, the coding, the interrupt service routine was very, very short. I'm just going to toggle port A pin 1, increment T2, acknowledge the interrupt by clearing the flag, then get out. The reason for this line of code is really not necessary at this point, but in 2 days we'll be looking at adding more interrupts. This says, if I'm in the interrupt service routine at address 8, somebody called the interrupt. Who was it? Was it timer 2? Was it timer 1? Was it timer 0? This will be used a little bit later on when we have multiple interrupts. It's a little bit redundant right now because since only timer 2 is turned on, if I'm in the interrupt service routine, I know it was timer 2. So in summary, what timer 2 interrupts do is they're a way to keep precise track of time, such as measure time to 1 millisecond. The best I can do practically is every 0.1 millisecond, 0.0001 second. Or I can output a precise frequency. It now looks like I've got two programs running in parallel. I've got the interrupt running every n clocks. I've got the main routine running. With that, I can update the LCD display, read the push buttons, do stuff like that, plus have the interrupts running in the background. So that's timer 2 interrupts. What we'll do next lecture is give a couple examples of what you can do with timer 2 interrupts. But that's lecture number 18, timer 2 interrupts.